Hello, everyone, and welcome to today's OSA Technical Group webinar, Conformal Optical Coatings by Atomic Layer Deposition. My name is Hannah Walter-Pylon. I'll be helping to moderate this webinar on behalf of the Optical Society. We're very excited to have Sammy Snack and John Ron from Beneq joining us for this webinar, which has been organized for you by the OSA Thin Films Technical Group. While we wait for all of our attendees to join us here in Zoom, I wanted to take a moment and tell you a bit about OSA Technical Groups. OSA technical groups integrate vibrant and active communities for all of our members to participate in. We offer members more than 40 different technical groups to choose from, and each of these groups are led by OSA members who volunteer their time to organize events that are tailored to your interests, such as today's webinar. In fact, our technical groups have been hosting webinars regularly since 2013, all of which are available for you to view on demand on our website. So you can find out more about the technical groups, find out about our upcoming activities, and also access our library of over 150 on-demand webinars by visiting us at osa.org/technical groups. Now, before we start with our presentation, I want to note that we will be addressing your questions at the end of the talk today. We encourage you to submit questions for our presenters throughout the webinar, though, and you can do so by clicking on the Q&A button at the bottom of your screen. You'll then be able to enter your question in the pop-up box, and you're also going to see questions from your fellow attendees in the Q&A box. So if there's a question you'd like to see answered during the Q&A session, hit the thumbs up button beneath it to let us know. Now, finally, when you disconnect today, you're going to be prompted to complete a short survey and provide us with your feedback. You're also going to be able to download a PDF copy of the slides used in today's presentation directly from that survey page. We are also recording this webinar, and we'll send you a link to the recording and a link to the PDF copy of the slides within 48 hours. So now it's my pleasure to turn the floor over to Ju Wang, who is the chair of our Thin Films Technical Group. Ju's going to tell you a bit more about the technical group he leads and introduce you to our presenters. Ju, the floor is all yours.
Thank you, Hannah. Before I introduce our invited speaker, I'd like to share some information about the technical group. And next slide, please. And just a screen capture of the technical group. We have a team to serve the community. And next one, please. No matter where you are in industry, university, or institution, we would like to connect you to the thin film community and to share the frontier of the thin film and to correct the fundamentals and exchange the technical know-hows. And we have been doing this several years and try to get a speaker from different area, university, research institution, and industry. Next one, please. And there are different ways to connect with us. You can go to OSA website to find the thin film technical group. And also we have a LinkedIn account, and you may also join us for the OSA Optical Interference Coating Conference in person next year. Now it's my pleasure to introduce our invited speaker. We have two today, and Sam Snack and John Ron. Sammy is a business executive at Beneq, and he got his master's degree in chemical engineering, and he introduced ALD to various fields from photonic optical coating and semiconductors. John Ron, from other hand, is focused technically on ALD for optics and photonics at Beneq. He has a PhD degree from in the field of electronic engineering, and he published several ALD-related papers in natural communications and SES photonics. It's really our pleasure to have the two invited speakers. And now, Sammy and John, it's your time. Thank you.
Hi, my name is Sami Snek. I have been working with ALD for optical coatings more than 10 years now. And over the recent years, I'm very happy to see that more and more people are getting excited about the same thing.
Hello everyone, my name is John Rönn. I have a PhD in photonics, and over the last 7 years, I have worked with ALD for both optics and photonics. And over the recent years, I've had the pleasure to publish some of my work in very highly cited journals, such as Nature Communications and ACS Photonics. So on my behalf, I'd like to thank you to coming to this webinar that titles Conformal Optical Coatings by Atomic Layer Deposition. So first, Sami will start this presentation, and I will continue after Sami. And after my part, Sami will still continue this webinar.
Okay, first we start with a little bit of a background. So ALD has not been so far very widely used for optics, but it has been used for many other things. So it's especially in the microelectronics, semiconductor area, ALD is very, very widely used and enabling a lot of products that we all use every day. And also in various other fields within nanotechnology, ALD is quite well known. Also within optoelectronics, there are various places where ALD is being utilized. The ALD is getting more popular overall, so a number of citations related to ALD overall are growing quite rapidly. And this tells that ALD is getting into more new areas all the time. And but the question is that will ALD do the same also within the optics and optical coatings area? It has clear advantages, which also kind of shown here on this slide, meaning that the step coverage is great, so it can make very uniform films on complex substrates. But also the drawback is here. It's very slow compared to competing methods. So that's really the question that does ALD have enough benefits to counter those drawbacks. And that's what we are going to be talking more about today. But starting first with the principles of ALD. What is ALD? Atomic layer deposition process is based on saturated surface reactions. So it's a chemical process. 2 precursor chemicals are needed, and they are introduced onto the surface that we are coating one by one, separated by a nitrogen or inert gas purge phase. So we need these 2 chemicals. In the first step, which is the first pulse, there is the first precursor that this chemical reacts on the surface. As long as it can find more available surface sites, it will keep reacting and then becomes automatically saturated, so the growth stops. It cannot grow on itself more, so it will just generate one monolayer. Then during the purge step that will follow, the inert gas, nitrogen, will remove any remaining first precursor material from the gas phase, leaving only the ones on the surface. And then on the third step, we introduce the second chemical, so it's another pulse, typically an oxidizer. Like in this example here, it's water, very common oxidizer. So that water vapor comes in, reacts again on the surface. Byproducts are generated, and they are gaseous. They go away with the inert gas flow. And again, the reaction will continue as long as there are active sites available. And once completed, growth stops automatically, and we have completed one kind of monolayer of the material that we are depositing, so one ALD cycle. So after the second pulse, there is another purge phase needed, so that the remaining moisture, water vapor, is removed from the gas phase. And then this ALD cycle, consisting of these 4 steps, pulse, purge, this can be repeated as many times as we wish to reach the desired film thickness. And it needs to be usually repeated many times because one ALD cycle only gives you about 1 angstrom or 0.1 nanometers, roughly, the thickness. So you need to be repeating this many times. And the benefits really can be derived from this, the growth mode. So because it's surface controlled, ALD will make conformal coatings on whatever the surface geometry is. And also, we already mentioned that it's slow. Yes, it is, because we are building these atomic layers one by one, and atoms are very small. So it's all coming from the very nature of the process. But comparing to other processes, like more widely used in the optical industry, like PVD, especially sputtering, evaporation, these types of processes, or chemical vapor deposition, CVD process, which is very much related to ALD, but still different. ALD can make much more uniform coatings on complex shapes. So that's really the key benefit of ALD. Surface controlled, not source controlled, or kind of line of sight type of thing. Yeah, ALD has been quite widely studied already, and a lot of materials have been published. So this is a periodic table of elements showing all the different things that people have deposited with ALD. So there is a lot of things that have been already done. However, it's good to notice that only some of these, few, actually minority of these, are really scalable to mass production scale currently. Okay, then next we are going to hear more about batch type of ALD from John.
Okay, thank you, Sami. So as Sami mentioned, the conformality of ALD is one of the most important features of the technology. In some applications, the surface to be coated can be so complicated that there is simply no alternative way of depositing a reasonable film with any other technology. In many of these cases, one typically aims to deposit only a few tenths of nanometers of high-quality film, such as when passivating a surface, for example. However, when it comes to optical applications, much thicker films are often required. However, for ALD, depositing thick films is not trivial because the layer-by-layer growth mechanism can be extremely time-consuming. So having said that, the purpose of the next two sections is to demonstrate how we at Beneq have been able to increase the throughput of ALD while still maintaining the exceptional features of the technology. So, although ALD or the typical ALD processes in general suffer from low deposition rates, ALD itself is actually a very highly scalable technology. This means that the throughput of the technology can be increased, for example, simply increasing the substrate size, for example. So here you can see an example of Beneq's technology used to coat a 1200 × 1200 square millimeter glass substrate with zinc oxide, zinc sulfide buffer layer. Of course, coating a one large substrate is not very practical in many applications, but it still demonstrates how well this technology can be scaled up. Nevertheless, in many optical applications, one is typically looking to deposit multiple wafers or coat multiple wafers or substrates in a single run. For this purpose, we have developed our batch ALD equipment, P400A and P800, that are ideal for this purpose. So if you take a look, for example, inside our P400A tool, we can see that a very large deposition chamber can be included within the reactor. This deposition chamber can hold up to 8 square meters of substrates, and all of these substrates can be coated with a uniform and conformal film in a single run. So here you can see a video of how this is done in practice. So now that we have demonstrated the capability of using ALD for mass production, let us now move on to what kind of optical coatings we can and typically produce with these tools. So in our typical optical applications, we use very low loss and particle-free materials such as silicon dioxide, aluminum oxide, hafnium oxide, tantalum oxide, or titanium dioxide as our basic building blocks. By combining these materials, either as bi- or multi-layer structures, we can realize most of the classical interference coatings, such as anti-reflective coatings, highly reflective coatings, edge pass filters, or band pass filters, basically at any spectral region of light. Of course, we can produce other optical components, but these are the ones that are currently in very high demand in many optical fields. So by combining the BATS ALD equipment and our low-loss, high-quality and particle-free building blocks, we can realize many optical functionalities even on the most challenging surfaces, such as those found in the microscale, such as micro and nanostructures, gratings, or sidewalls. We can also coat challenging structures found on the macroscale as well, such as freeform optics, high curvature lenses, or complex 3D shapes, such as optical domes, tubes, or rods. So let us now take a few case examples that demonstrate some of the exceptional features of the ALD technology in optical applications. We dive firstly into 3D structures. So as we know, large and complex 3D shapes, such as optical domes, are examples of components that are structures that are very difficult or even impossible to coat conformally within a single process. Of course, with traditional deposition techniques at least. To succeed in this kind of deposition, a tremendous effort needs to be put into, for example, twisting, rotating, or otherwise moving the structure between multiple processes. This, of course, leads to additional work as well as cost and is far from practical when it comes to mass production. However, this is not the case with the ALD technology. So here you can see an example of a large topless cube that have been coated with 3000 cycles of aluminum oxide. In this example, each side of the cube includes a glass substrate that have been analyzed with transmission measurements. The analysis shows that a very uniform and conformal film can be deposited throughout the entire object, with the non-uniformity being less than 0.4% over the entire structure. So let's take another example, a hemispherical or so-called optical dome. So again, this kind of structure is an example of a very complex 3D macrostructure that are very difficult to coat conformally with traditional deposition techniques. However, this is not the case with ALD either. So in this example, we use a 2-dome configuration as loaded into P400A reactor or deposition chamber as shown here. Each of these domes includes a 1-inch silicon substrate both face up and face down at the front, top, back, left, and right side of each dome. And then we can have additional reference substrates to compare the growth against a flat surface, for example. So by depositing 500 cycles of aluminum oxide in this configuration, for example at 300 degrees, here you can see the thickness results as measured with the ellipsometer. So on the upper dome, we can have very conformal and uniform layers, both face up and on the face down samples. So this means that also on the underneath, as well as on the top side of the dome, there is a very conformal coating. If you take a look of the lower dome, the results are basically identical with slightly thicker film throughout the dome. If you calculate the non-uniformity for this kind of configuration, the value is as small as 1%. Already a very good result. So what about if we go to lower temperatures then? For example, at 200 degrees. In the lower dome, both at face up and face down samples, we have again a very conformal and uniform coating with slightly thicker or faster growth rate, which is typical for this aluminum oxide process as the temperature is decreased. In the upper dome, the results are also basically identical, and the overall non-uniformity over this dome with being 0.7%, so a slightly better result actually at lower temperatures. If you go to even lower temperatures, such as 120 degrees, the result is actually even better as compared to the other previous cases. So a very uniform, thicker, and conformal film throughout the entire lower dome, as well as the upper dome as well. And if you calculate the non-uniformity for this kind of configuration, it's as low as 0.4%. And this is already comparable to the flat surfaces. So if we would have a similar kind of flat substrate, the results would be the same. So basically this kind of process, or the ALD doesn't even care if there is a complex 3D structure, so it still coats everything very smooth. So let's now move into completely different example, from macro scale to nanoscale. So as Sami mentioned in the previous section of this presentation, ALD also, or the layer by layer growth mechanism of ALD also enables one to specifically engineer the material properties of the deposited films. So this is one of the key aspects in developing efficient active devices, such as lasers and amplifiers, for example. So in this example, we studied the interplay between two materials, erbium oxide and aluminum oxide. So erbium, which is one of the 15 lanthanides, is actually one of the most studied materials in optical applications, simply because it lies in the heart of optical communication networks as a part of component known as the erbium-doped fiber amplifier. By using both these materials, erbium oxide and aluminum oxide, we can fabricate an optically active material, erbium-doped aluminum oxide, using our ALD processes. So for the actual ALD processes, we use a TMA water process for the aluminum oxide and erbium THD3 and ozone for the erbium oxide process. So the reason why I am showing these precursors here is because the size and geometry of these precursors actually plays a very important role as to how efficient our erbium-doped material is going to be. So let me show you how. So we start our process by first with the erbium oxide cycle. So we pulse the erbium THD3 molecule on the substrate, followed by a purge. So now, because this size of this erbium THD3 molecule is so large, it actually prevents nearby surface sites to be occupied by another erbium molecules. This is simply because molecules and atoms cannot occupy the same space. So now we continue our process by pulsing ozone, followed by a purge. The ozone actually purges and burns these organic ligands away, and basically we are left with a submonolayer of erbium oxide on the surface. And in this erbium oxide, we can have a controlled distance between these erbium ions, and basically determined entirely by the size of the THD3 molecule. But why is this so important? It's because ideally in a laser crystal, one needs to have a sufficient separation between the dopant atoms. Otherwise, they will just re-emit and reabsorb all the outgoing photons in your system, which leads to very decreased efficiency. So now we continue this process with the aluminum oxide cycle. So we pulse TMA and purge, and pulse water and purge. And because the size of this TMA molecule is now much smaller, a much more denser network of aluminum is formed on the surface. So the end product is a submonolayer of erbium-doped aluminum oxide, where the erbium distribution is actually controlled. So in this way, we can actually find the optimal concentration for the erbium in order to increase the efficiency of our laser medium. And now we typically continue this process with subsequent aluminum oxide layers, because we want to ensure that there is, again, a good enough separation between the erbium ions in the vertical direction as well. So here we have studied the photoluminescence response of different materials, where the number of aluminum oxide cycles in each layer before another erbium oxide cycle is released changes. So if we start with the lowest concentration for the erbium, for example, by introducing 12 cycles of aluminum oxide, we can see that the photoluminescence yield is the smallest. So now we start to decrease the number of aluminum oxide cycles. So we basically squeeze the erbium ions closer together. We can see that the photoluminescence yield actually rapidly increases. However, there is a threshold how much we can increase the photoluminescence yield, and you can see it here in the B figure. So once we start to decrease the distance between the erbium ions too much, we actually start to get diminishing returns. So this means that there is not enough separation between the erbium ions in the vertical direction, and the result is less efficiency in the laser crystal. So this basically allows us to completely optimize our laser media, which is a very important feature of the ALD technology as well. So having optimized this material, we just need to find a platform or device where we want to deposit this material. In this example, we use silicon nitride slot waveguides on a silicon photonic platform, as you can see here. So typically in these slot waveguides, the slot region is very narrow and very difficult to coat conformally with traditional techniques. However, for the ALD, the outstanding conformality actually ensures that we can coat the entire waveguide cross-section very smoothly and conformally, as you can see here. So even the slot region can be coated very smoothly. So if we analyze, for example, how the light is now propagating in these kind of structures, we can see that, for example, for the TE mode or the transverse electric mode, the light actually couples inside our laser medium. So most of the light is going there, so it can pump and then re-stimulate photons to amplify itself. And this is what we studied in one of my works. Basically, we studied waveguides with different lengths and showed that up to 20 dB or decibels per centimeter could be obtained with this optimal material, this erbium-doped aluminum oxide materials. And this work has been published in Nature Communications, and you can find more information here. So as a summary of my part, I mentioned in the beginning that the throughput of ALD, although in general it is very slow, it can be increased greatly with batch ALD equipment. I also mentioned that many optical functionalities can be realized on even the most complicated surfaces found at both microscale and also at macroscale. And finally, I showed you that the ALD also enables one to specifically engineer the material properties of the deposited films, which find applications, for example, in laser technology, but of course, other areas as well. So now, Sami is continuing this presentation with a very interesting topic and shows you another way of increasing the throughput or the deposition rate of ALD with our newest addition to the ALD family, the spatial ALD.
Thanks, John. Okay, so then we talk about the spatial ALD and ultra-fast deposition with that. So first, starting with what we are really talking about here, kind of conceptually. So we have a so-called rotary spatial plasma-enhanced atomic layer deposition process. Yes, complicated. But anyways, so the substrates in this are placed on a turntable, and they are rotated through precursor zone and plasma zone multiple times. And it is faster to rotate the turntable compared to pulsing and purging the gases, as is done in the traditional way of doing ALD, which enables in this rotary process we can reach very high deposition rates and short cycle times. So as an example, using 200 RPMs, the ALD cycle time, which is that pulse purge, will be completed in 300 milliseconds. So here on the left side is the schematical drawing of this, and on the right side you see the actual image of a Beneq C2R system where this is happening. Okay, so that's the whole system there, and as said, based on this rotary spatial PALD process, which enables the high deposition rates, really up to micrometers per hour, which is very much for an ALD process. And also another kind of advantage or disadvantage, depends on the case, but anyway, a feature of this process is that it naturally makes single-sided coatings, whereas the traditional type of ALD tends to coat everything, also both sides of the substrate very easily. This tool itself, the Beneq C2R, can hold 7 pieces of 200 millimeter wafers. That's the kind of batch size that we have in it. And it can be used also not only for wafers, obviously, but also for thicker lenses and such things, even with thickness up to 30 millimeters. And it can make highly uniform films, which are suitable for optical coating. We'll hear more about that soon. And also for wafer applications, it can be equipped with a load lock or wafer automation. Yeah, so here you see more images on the right-hand side, also showing the inside of the system on the top left corner of those images. So you can see that first of all that this is where the substrates are on this turntable. We are actually now viewing through the plasma zone into the system, and you can see that the substrate here would be face up, so that's the orientation of the substrate. And yes, there are multiple of those. As mentioned, 7 pieces of 200 millimeter wafers, or a larger number of smaller wafers or other smaller substrates then can be placed freely inside that coated area. Yeah, the process pressure here is around 2 millibars or 2 torr level, and that's where the plasma system is working optimally. The bottom left picture shows how the lid of the system, the top, can open, and you have very good access to the system. This way you can manually do the loading and unloading of substrates, those non-wafer type substrates. And on the bottom right corner image, you see a load lock. So this is the port where the load lock is connected to. So this is where the wafer automation can also fit in. All right. Another important part of the ALD system is the precursor delivery. So that these chemicals are doing all the job for us. So this is where they come from. So in this C2R system, we have 4 canisters for the liquid precursors, and additionally 3 gas lines for the plasma. So each canister for those liquids is 3 liter in size and can be heated up to 120 degrees C, which opens up nicely quite a lot of possibilities for use of different precursors and thus depositing different film materials. More information available on our website, where you can check the video also in action. But what we can do with this sort of spatial ALD? So can we make good optical materials? Here is some work that we've done together with our partner Lotus Applied Technology, and this is showing the quite good optical materials with low optical losses. So silicon dioxide, titanium oxide, and tantalum oxide all have relatively low losses. So that's at least encouraging, and even materials that can be used for laser applications. Another important thing for such applications is the surface roughness. So this again study shows that we can make very smooth films with RMS roughness below 1 angstrom. So very smooth films on using these materials. And then the one big kind of question here is that we have now learned that ALD is very conformal. It's kind of perfect for that. Here is a test structure with an aspect ratio of about 20. So 6 microns wide and 120 microns deep. And this has been kind of coated for contrast reasons with tantalum oxide first, and then we are monitoring how the other films grow on this, and then we measure with the SEM and compare the thickness at the bottom of the trench to the thickness at the top of the trench. And we see that with silicon dioxide, regardless of basically our RPMs, even going up to 300 RPM, still we get perfectly conformal films, same thickness at the bottom and at the top. With tantalum oxide, we see that it's kind of perfect at lower speeds, but then at higher speed, it starts slowly to decrease to around 80% at the highest speed. And with titanium oxide, even at the lower speed, it's not like 100% perfect, but it's around 80%, and then will drop to around 60% at higher rates. So can make conformal films, so the film will go everywhere quite nicely. But when making optical coatings in such structures, then care needs to be taken, definitely, that it's not automatically kind of 100% uniform everywhere. Then an example we made on an AR, so AR coating with relatively simple design. So it's 4 layers done at low temperature, both for the polycarbonate and glass substrates at 200 RPM. It took about 18 minutes to deposit the the stack, and the results were well, as expected, naturally, but showing quite nicely the very good performance, especially on the glass, and also on polycarbonate. Quite good performance can be reached with this. And this is just a demonstrator of that we can actually make stacks and build the optical coatings. Another kind of critical question here is that how uniform can the process be on the large scale? So we know that we can make stacks on small samples, but how about larger? Here we use a 200 millimeter wafer as a large area substrate, and we see that depending on the RPMs, so the speed we can reach with taking the non-uniformity over the wafer, we are somewhere around 2% range, which would mean about 1%, 1 sigma uniformity. But we are at around 2% uniformity over the whole wafer. And it naturally is so that it is more uniform in the direction of rotation. There is actually very, very little variation in that. So it's only really in the radial direction. So which means that for smaller substrates, like 100 millimeter substrates, we can reach much better uniformity, and we can find really, really uniform areas for smaller substrates. One thing to note here is that just again, kind of practical thing, that it takes only about 4 minutes to deposit this 100 nanometer aluminum oxide film at 200 RPM. So compared to the other ways of ALD, this is really, really high speed. So just to summarize the rotary spatial PALD part, very high deposition rates, and offers the benefits, generally the benefits of plasma enhanced ALD in production scale, which are the single-sided coating, some materials that are only possible with plasma enhanced ALD, like silicon nitride. Also allows lower temperatures to be used for important materials like silicon dioxide, as an example. Plasma also gives us possibility to control the film stress better than the thermal process, and these are the main reasons for anybody to consider using the rotary spatial PALD process. Yes, thank you. And then we continue with finally the few words about Beneq itself. So who we are, where we come from. So we say that Beneq is home of ALD, and why is that? Well, because this is where it all started. So ALD was invented, well, almost 50 years ago, but it was really invented to do what we are now doing, which is the electroluminescent displays, shown here on the top image. And that's part of Beneq's business nowadays. We use ALD to make such displays. And we have been using ALD here for more than 40 years already. And the building shown here is where we are, our headquarters, and there we have more than 40 ALD systems in-house used for various different things. And being in operation, production use 24/7 for decades already. So that's why we say we are home of ALD. Currently, our company has more than 170 people, and is growing very, very fast, thanks to the growing interest for our ALD. And these were the systems that we mostly talked about today. So the P400A, the thermal batch system, and then the C2R rotary plasma system. But that's not all that we do. So we offer a range of other equipment as well, different versions of the research scale equipment. Then we have semiconductor manufacturing equipment, cluster tools, and those batch tools, and the spatial ALD systems that we touched today. There is also a roll-to-roll system shown on the bottom right corner that's based on another type of spatial ALD process. In addition to equipment, we offer coding services. So we have equipment. Some of those 40 pieces of equipment are used for coding services. And also some of them are used for what we call development services. So we can develop solutions for our customers in deep collaboration with the customers. So we have dedicated teams to do the coding service and also team to do the development service. So the question then is that, do you have a product that would benefit from an optical ALD coding? Well, if yes, we are looking forward to hearing more from any questions from you. Thank you very much.
All right. Thank you very much to Sammy and John for that presentation. We will go to our question and answer session now. So if you have a question that you have not yet submitted to the Q&A box, now's the time to do so. All right. And John and Sammy, you'll just want to make sure to unmute yourself so we can hear your responses. Our first question came from Parth, and it asks, how do you control the CVD component of ALD reaction in the batch reactor?
Okay, well, maybe I can take this one. Thanks. Good question. The key is just to keep those two gases that we use as the precursors, keep them separated, not let them mix in the gas phase. So it means that the purge step is the key there. So we just need to have long enough purge times or efficient enough purge phases to keep those two gases separate. It's also how easy it is to get rid of extra gas in the gas phase depends also on the temperature that we are at. So I'm sure that many people are used to kind of sticky water in the system and trying to get that out. Of course, it'll be easier if we are at higher temperature. So that's kind of one thing actually that is limiting or kind of determining the deposition rates is that typically it takes more time to purge than pulse the material.
All right, thank you very much, Sammy. So we'll move on to the next question from Dimitri. And he asks, how is the uniformity at 3D objects for materials beyond aluminum? And they mention especially silicon, halcyon, titanium, and tantalum.
Okay, I can take this one. Yeah, that's a good question because like for ALD, the aluminum oxide is the most studied and the most traditional material. Typically, it grows everywhere. It's very uniform. And of course, we are also producing, also interested in other materials as well. Typically for these other oxides, the results are not that much worse, actually closer to 1 to 1.5% non-uniformity, for example, in the same configuration that we just presented.
All right. And I'm going to move down to another question from Doug, which asks, what temperatures are required to deposit the hafnium oxide in a batch reactor?
I can take this one as well. Typically, we use 250 degrees around, but we can go less than 200 as well.
All right, thank you. So the next question today asks, are there practical precursors for metal coatings, for example, price, uniformity, deposition rate, etc.?
Sami, do you want to take this one?
Sorry, I think I missed part of that. So could you repeat the question?
Not a problem. So the question is, are there practical precursors for metal coatings, for example, price, uniformity, deposition rate, etc.?
Or metal coatings?
Yes.
Yeah. So if I understand the question now correctly, so the metallic coatings, not metal oxide coatings, which is kind of more normal for ALD. There are some metals that we can deposit, mostly noble metal, such as iridium or platinum, rhodium, these kind of things. Of course, precursors are highly expensive. The processes actually work quite well, but it's really quite limited to those noble metals. There is one quite well working process also for tungsten, but that's about it. So then metallic kind of properties we have with titanium nitride coating also, but that's depends on the definition whether you consider that as metal or not. But that's so the typical things like aluminum or titanium are just not really possible with ALD. The chemistry just doesn't work.
All right, thank you. And that attendee also asked, is the precursor consumption for fast ALD comparable to the classic ALD?
Yeah, it is really a if we kind of compare it, that of course the kind of if you have a higher deposition rate, you will be consuming the precursor faster. But if you kind of per the surface area that you are producing, then the consumption is same. So if you are doing a same amount of square meters and with the same thickness, then the precursor consumption is pretty much the same. There might be a slight benefit for the spatial ALD, because essentially you are not coating all the chamber walls. You are just coating the kind of donut-shaped area there. But in practice, if comparing this method to a large batch where anyway you have usually mostly your substrates and not so much chamber walls, then the difference is in practice not big.
All right, thank you. So we'll move on to the next question from Jaden, who asks, they say, it's been our understanding that thick multi-layer coatings like mirrors and filters suffered from tensile stress failure in the past with ALD. How did you solve this problem?
Okay, that's maybe, well, I can start, maybe John can fill in if he has more information. So this question was suggesting that it's kind of well known that the coatings suffer from tensile stress. That may be partially true and partially maybe not necessary, but typical ALD coatings do have tensile stress. Maybe out of the common materials, silicon dioxide is typically has the other way, compressive stress, so that can balance things. If we can make stack using tensile and compressive, so then it'll kind of balance things out. Also, very much depends on which substrate materials we are using. So the CTE of the thermal expansion coefficient of the substrate is very important. So so if that is matching quite well with the films that we are doing, then usually there is much less problems with stresses. As anyway we are doing the films at elevated temperature and then cool down, that generally tends to create stress, cooling down to room temperature. And yeah, then of course, as I think it was mentioned in the presentation, that if we are using the plasma enhanced ALD processes, that gives us also more possibility to control the stress. So the film stress can be influenced and kind of controlled with the plasma parameters. Yeah, that's I think my input on this topic. Maybe John wants to add something.
Yeah, basically also in thermal ALD, you can modify the surface with precursors such as ozone or ammonia, for example, to reduce the initial stress on the between substrate and the thick optical coating.
Yeah, maybe one thing I'd like to add also, one kind of clever way of kind of escaping the stress problem is what has been also utilized already is that if you use sometimes stress is causing a bending of the substrate, and that's the problem. With ALD, we can coat both sides of the substrate with identical film. So we design the optical performance that way that it's actually two-sided coating, and there will be kind of identical stress on both sides, which helps to keep the substrate flat.
All right, thank you both for addressing that question for us. We have a question from Ju that came into the chat and asked, any development of ALD fluorides for optical coatings in the deep UV spectral region? And what are the main technical challenges?
All right, maybe we can both try for this one as well. I'll start. So fluoride, yes, we do have some work on fluorides. And generally it is the kind of, these are less studied chemistries. So that's kind of the ALD process itself hasn't been studied that much, and probably plenty of room for improvement on that. But typical material like magnesium fluoride is something that we already quite well can master. But anyway, so there is still probably quite a bit of work to be done on that department. Maybe John, if you'd like to add something.
Yeah, so basically we have a lot of work going on in that direction. So it's a good question, and it's a tricky topic, but we are moving there at least. So.
All right, thank you both. I think that answers all the questions that we had come in from our attendees. So we'll go ahead and wrap up now. Everyone, when you disconnect, please remember to complete the short survey and provide us with your feedback. You'll also be able to download the PDF copy of the slides from Sammy and John's presentation directly on that survey page. We'll also email you directly within 48 hours to send you the link to the recording and also the PDF copy of the slides. So I'd like to thank Sammy and John for being here and presenting for us today. And I'd also like to thank you and our Thin Films technical group for organizing this webinar for all of us. We hope you enjoyed today's presentation, and we will see you at our next webinar. Thank you all for joining, and have a great rest of your day. Bye.
Thank you very much.